Hello everyone, welcome to the Audio SoC SDK Introduction. Today, I would like to introduce you the SDK of next generation Bluetooth audio SoC platform of Realtek. Today's presentation covers the following topics. First is SDK introduction, including SDK file directory structure, development environment, toolsets, and documentation. Second is software architecture. And the third to fifth are platform, peripheral, framework. This report is mainly some introductory content, so for some of the technical details, you can understand them in detail through the documentation inside the SDK. Now let's go over the structure of the SDK itself. The SDK is comprised of 6 directories: board, dock, inc, bin, src, tool. In the board directory is the EVB subdirectory, which contains sample app projects such as RWS, BLE, IO, SPP, and other sample projects. For example, you can check the BLE projects for examples of how to use BLE. Next, we have the dock directory. It contains documentation for things such as the API and the user manual. Following that is the include directory, which contains our libraries. The libraries include app, Bluetooth, file system, framework, IO, OS, platform, and service. App includes ROM application layer related APIs, Bluetooth contains Bluetooth related APIs, file system contains file systems related APIs, and etc. To contrast, the bin directory contains generated lib files and binary files. Then we have source, which is where the source files are contains. For example, if you go to sample RWS, you will find the source files used for the RWS sample project in the board directory. Next, we have the tool directory, which contains important tools to use for the IC. The tool to download the flash image onto the IC, debugging tools, the MCU configuration tool, the DSP configuration tool, the MP tool will all be found here. Finally, we have the trace directory, which includes trace files to decode encoded output logs from UART interface. Our IDE development environment is Keel, its version is 5.26. Some toolchains used, such as compiler, assembler, linker, etc. Version is 5.06 update 6, 750. We recommend our customers to use this version to do development. Different SDKs support different ICs, and each IC needs to use a different target and flash map to compile and generate the RWS app image. The following table lists the targets and flash maps that need to be selected for each supported IC. Note here that if you select the wrong target and flash map, the compiled image may not work when burned to the board. Now to go into a bit more depth, here are the tools provided by the SDK. First, we have the MCU config tool, the DSP config tool, and the ANC design tool. These are configuration-related tools, and whether you need them will depend on the IC you are using. Next, we have the MPPG tool, which is used for downloading the image onto the IC. The debug analyzer is used to read and extract logs from the IC, which can be analyzed later. The ANC-MP tool is used for adjustments. Then there is the MPKit setup package, FastMP tool, BTMP tool, all tools related to mass production. In addition to these auxiliary tools on Windows, we also have an application Audio Connect that supports iOS and Android phones. Through this mobile app you can configure and control the headset, such as changing the name, adjusting the EQ, doing OTA upgrades, etc. This Audio Connect we also provide the corresponding SDK for customers to customize their own functions. Here we have the software architecture. The diagram we have here is color-coded and labeled on the bottom. The green color ones are hardware modules, the next deep blue squares are third-party libraries, the middle one is implemented by us, and the right one is what the vendor will implement. Here, on the right is the gap, which is an abstraction layer which allows communication between the dual-mode stack and profile/applications. The framework library is comprised of the Device Manager, BT Manager, Audio Manager, and Remote Manager modules, which contains the API needed to develop audio and Bluetooth products. LE Audio Library implements generic audio framework of LE Audio. In the middle we have the platform features, which includes things such as OTA/DLPS/charger, etc. To the left of that we have the OS interface, which provides the ability to manage OS components in case the application needs to debug OS components, or you need to migrate to a different OS. Lastly, on the very left is the I/O drivers, which provide mechanisms for applications to interface with the BT Audio SoC onboard peripherals without accessing the registers. Next, let's look at the SDK documentation, which is very important. We recommend our customers to read our SDK documentation carefully after getting it. We provide a unified SDK documentation which is generated through Doxygen to help customers get familiar with the BT Audio SoC SDK, including user manual, application notes, API reference, and license information. The user manual provides a series of documents detailing various aspects of the system such as architecture, platform, memory, flash, secure, toolsets, etc. Application notes is a detailed description of each module of the RWS app. We provide dozens of application notes, which provide detailed descriptions of all aspects of the app, so that users can become familiar with our SDK and the code of the RWS app as soon as possible. API reference is generated by Doxygen annotations. Each API has a detailed usage description. Users who are not clear about the use of the API can consult this section. We have just introduced the software architecture of the SDK from the perspective of modules. And next, from the perspective of tasks, we are a FreeRTOS-based multitasking system. On the left and right are the timer, flash, and idle tasks, which are both provided by the FreeRTOS. In the middle we have upper stack tasks, which provides protocols defined above the HCI, and lower stack tasks, which implement those below the HCI. Lastly, we have the application task, which handles user application requirements besides profiles and services above the gap layer. Tasks also have a priority. You can see their values on the bottom right, with timer and lower stack having the highest priority, and idle having the lowest. Now we have the application process flow. Once again, these are color-coded. The ones in blue have already been handled by Realtek, while the ones in yellow will have to be handled by the vendor. On the left here, we have the boot process, config, board, gap, framework, driver, profile, power manager, other modules, and task init. This will initialize important settings and parameters such as the pinmux and pad settings and gap-related parameters. Once that's done, it will start the OS scheduler. Now with the OS scheduler running, the app task will start running. What it does is that it loops infinitely, waiting for messages from the application layer, and once it receives one, it determines whether to give that message to the BT stack handler, framework lib handler, or the app handler. Lastly, when there is an interrupt, for example, from UART, GPIO, or a key, then it will create and send a message to the app task, which once again, will parse it and distribute it. Now I will introduce the memory system of RTL87X3E generally. RTL87X3E's memory system consists of ROM, RAM, flash, and eFuse, which has flexible configuration mechanism. The flexible configurability and extensibility let RTL87X3E support a wide range of applications with different memory usage. Many fundamental functions are built in ROM, read-only memory, such as bootloader, RTOS, BT stack, and I/O drivers. The ROM code is located at 0x00000000, 0x0000000. RTK offers abundant APIs for user to access most of the ROM functions, which can improve users' development efficiency and reduce code size. RTL87X3 has 5 types of RAM: ITCM1, DTCM0, DTCM1, buffer, and DSP RAM. And ITCM1/DTCM0/DTCM1 SRAM or internal SRAM of ARM core, which are close to CPU to get good performance. On the contrary, buffer SRAM and DSP share SRAM are relatively slow for CPU access. All types of memory could be used to storage data and execute code. ITM1 is recommend for RAM code and DTCM0/1 are recommend for storage data. RTL87X3 supports external SPI flash by installing an SPI controller OS PIC. Each SPI flash on board is controlled by SPIC, which has a mapping memory to it. The maximum flash size considering different SPIC mapping memory range is as follows: 32 MB for SPIC-0 and SPIC-1, 8 MB for SPIC-2, and 256 bytes for SPIC-3. Also, with cache, both data reading and code execution efficiencies on SPI flash could be largely increased. Moreover, Realtek offers the low-level flash driver, FTL, and high-level flash storage APIs. As mentioned above, the global and heap regions of memory are configurable, and the corresponding configuration file is located in the SDK /board/EVB/RWS/RTL87X3E/directory is the mem_config.h file. First, if the user wants to adjust the global size larger, simply adjust the app_global_size larger. Second, if you want to increase the heap size, you need to turn down app_global_size. Note that the total sum of app global and heap is unchanged. RTL87X3E has a two-layer flash layout which indicates the start address and max size of images in flash. First, the configuration of OEM header and boot patch are fixed in ROM, which can't be changed. Second, the configuration of platform_ext, lowerstack_ext, and upperstack are fixed when SDK release. Third, the OEM header and boot patch header record the layout of high-layer images, except images in banks. Fourth, the OTA header fixed at begin of BANKX area defines the layout of images in the same banks, low layer. The high-layer illustration of flash layout is shown in the following figure. Next, we have the layout for flash. At the start is the reserved space, followed by the OEM header. This contains a header and a payload, which defines the rest of the layout for the flash and some params. Afterwards we have the rest of the flash, the boot patch, bank 0 and bank 1, FTL, backup data 1 and 2, OTA temporary address, and the hard fault handler. Next, if we look inside bank 0 and bank 1, we'll see that they have an OTA header, which contains its own header and payload, shown in more detail on the right at the OTA bank 0 header. Then, we have the payload, which starts with the flash secure bootloader. The details of this payload are also shown in the right, in the OTA bank 0 payload. In this payload, the FSBL and the ROM patch cannot be changed, but the rest can. FTL flash transport layer is used as abstraction layer for BT stack and user application to save read/write data in flash. The purpose of FTL is to make it easier to modify the data stored in flash. If physical address is used directly, user must erase the entire page when the value of a physical address needs to be modified. The FTL space cannot be directly accessed by a physical address. It only can be accessed by a logical address. With FTL, user can directly modify the data corresponding to the logical address. The relationship between the logical and physical addresses is as follows. The maximum value of the logical address is the physical address minus 4 kilobytes and then divided by 2. The customer can adjust the size of the FTL by adjusting the size of the flash map. The variable app_cfg_nv, located in the file app_cfg.h/c, in the app is what exists in the FTL. We also support low power mode. Right now, the system platform and the BT Mac can enter low power mode independently. This means that if you are not using Bluetooth, then it can enter low power while the system platform remains active and vice versa. The system platform supports 6 different power modes, while the BT Mac supports 2. Users are able to update the images over the air, that is referred to as OTA. BT Audio SoC supports 2 OTA modes, one is for iOS, OTA via BLE. Another is for Android, OTA via SPP. Now let's introduce the OTA dual bank. Having a dual bank offers you protections from unexpected mishaps, such as the power suddenly getting cut off. The left bank shows dual bank OTA over SPP while the right one shows over BLE. These are the peripherals that we support: 64 GPIOs, 3 I2CS, IR, key scan, 12 timers, quad decoder, RTC, 3 SPIs, LED, 4 UARTs, ADC, and GDMA. Framework is composed of System Manager, BT Manager, Audio Manager, and Remote Controller Manager. It provides a rich API set for customers to develop audio and Bluetooth products. System Manager (SISM) is the main component for the interoperability between application and framework. Application shall use API sys_manager_init to initialize System Manager. The parameter EVT_handle is used by the framework to send messages to application. Below is an example code for framework initialization. Each application component can register SISM callback into framework with API sys_manager_back_register. If any SISM event t_sys_event occurs, framework will notify every SISM callback registered by application. BTManager (BTM) provides more convenient and high-level APIs for Bluetooth manipulation. You are encouraged to use BTManager APIs rather than using GAP and Profile APIs directly. BTManager divides APIs into two subsets: BT-Link and Device Manager APIs, BT Profile Manager APIs. Audio Manager (AM) provides audio manipulation APIs. Audio volume control APIs are defined in audio. Ringtone control APIs are defined in ringtone. Voice prompt control APIs are defined in voice prompt. TTS control APIs are defined in text-to-speech. EQ effects control APIs are defined in equalizer. Remote Controller Manager (RCM) provides interfaces for application peer-to-peer between identical local and remote side. This module focuses on P2P session setup, P2P information exchange, and P2P role swap. It should be noted that the memory and flash data mentioned in the slide above are based on the RTL87X3 MCU SDK, version 2.10.3.4 version of the SDK. Subsequently, if the customer gets a new SDK, there may be some data that will change. For more details, please read the SDK documentation carefully. If you have any questions, please feel free to contact us. Thank you all.